antennas. There are different types of antenna. First one is monopole antenna. It is made with single wire. Dipole antenna. It is made with two wires. Loop antenna. The antenna is shaped in loop shape. That's why it is called as loop antenna. Next one is angular antenna. It is a basic and widely used antenna for broadcasting television signals. Next one is horn antenna, parabolic antenna. These antennas are used at very high frequency ranges. Next, lens antenna, helical antenna, and microstrip antenna. These antennas are used at ultra high frequency ranges. Now, I would like to give brief introduction on Aggie-Muda antenna. Aggie-Muda antenna consists of reflector, director, and a driven element. It is unidirectional antenna. The operating frequency range is 300 MHz to 3 GHz. Basically, Aggie-Muda antenna comes under non-resonant antenna. The main difference between resonant and non-resonant antenna is in non-resonant antenna, the directional pattern is unidirectional pattern. In resonant antenna, the radiation pattern is bidirectional radiation pattern, and the operating frequency range is varies in non-resonant antenna, but it is varies in resonant antenna, but is fixed in non-resonant antenna. It represents the pictorial form of the Aggie-Muda antenna. In this, we are having a reflector element, driven element, and a number of director elements. This is the best example for parasitic element array antenna. Advantages of Aggie-Muda antenna. It is having high gain and good front to back ratio. It has narrow bandwidth. It is a fixed frequency device. Greater directivity due to director and reflector elements. Next antenna is the long periodic antenna. A unidirectional antenna in which the length and the spacing of the elements increase logarithmically from one end to other is the long periodic antenna. It is frequency range is independent antenna. The frequency range is varies VHF and UHF bands. The picture representation of the long periodic antenna is shown here. Here we are joining the two wire antennas and it gives the long periodic antenna. The direction is taken from the angle of vertex. Advantages of long periodic antenna. It is a broadband antenna. It is unidirectional antenna. It is frequency dependent antenna. Its frequency is independent antenna. Next one is the helix antenna. A conducting wire in the form of a screw thread fed by power source is the helix antenna. The feed line is connected between the bottom of the helix and the ground plane. Helix antenna is omnidirectional antenna. Omnidirectional means the signal is covers in all directions. The frequency range is in between UHF and VHF and UHF bands. Applications of helical antenna is satellite communication, space communication, and space probes. For telemetry applications also, helical antenna is used. Next one is the parabolic reflector antenna. This is used to convert spherical wave into plane wave. The feed antenna is called primary antenna and the reflector is the secondary antenna. Frequency range is 3 GHz to 30 GHz. This is the construction and the working principle of the parabolic reflector antenna. Here we are using the two antennas, the primary antenna and the secondary antenna. For secondary antenna, we are using the primary antenna we are using the horn antenna, and for secondary antenna we are using the parabolic reflector antenna. All the parallel rays are concentrated on the parabolic axis, and here we are taking the focal point and aperture plane also. Applications of the parabolic reflector antenna is for radar communication we are using, and for satellite communication also we are using the parabolic 100 to 1600 kilohertz. Applications: direction finding of signal propagation for radio reception AM and FM signals, for long distance point-to-point communication we are using. Next, the radiation pattern of the antenna. What is radiation pattern? Graphical representation of the radiation properties of an antenna is called the radiation patterns. It is depicted as a two-dimensional cross-section. So here it shows the graphical representation of the radiation patterns. First figure here represents the omnidirectional radiation patterns, and the figure B represents the bidirectional radiation patterns. Beam width. In radiation patterns, we are calculating the beam width also. For AWP antenna, we are having the H-plane radiation patterns and E-plane radiation patterns. Here we are calculating the beam width or identify the beam width. So the beam width in the radiation pattern of antenna, the main lobe is the main beam of the antenna with the maximum and constant energy radiated by the antenna. Beam width is the aperture angle from where most of the power is radiated. There are two main considerations of this beam width. First consideration is the half power beam width, that is HPBW, and second one is the first null beam width, that is FNBW. Half power beam width. According to the standard definition, the angular separation in which the magnitude of the radiation pattern decreases by 50% or minus 3 dB from the peak of the main beam is the half power beam width. In other words, beam width is the area. Beam width is the area where most of the power is radiated, which is the peak power. Half power beam width is the angle in which relative power is more than 50% of the peak power in the effective radiated field of the antenna is called the half power beam width. Next, first-null beam width. According to the standard definition, the angular span between the first pattern nulls adjacent to the main lobe is called the first-null beam width shown in the figure. Simply, FNBW is the angular separation quoted away from the main beam, which is drawn between the null points of the radiation pattern on the major lobe, is the first-null beam width. Antenna polarization. Actually, polarization is the orientation of the electromagnetic signal in the free space. Similarly, in antenna also, the electromagnetic signals in the given direction is defined as the vector orientation of the electric field component of the wave radiated by the antenna. In practice, polarization of the radiated energy varies with the direction from the center of the antenna, so that different parts of the pattern may have different polarizations. Polarization then is the curve traced by the end point of the arrow, representing the instantaneous electric field. The field must be observed along the direction of the propagation. The polarization may be classified as linear polarization, circular polarization, and elliptical polarization. The linear polarization is of the antenna helps in maintaining the wave in a particular direction, avoiding all the other directions. So it represents the linear polarization. Though this linear polarization is used, the electric field vector stays in the same plane. Hence, we use this linear polarization to improve the directivity of the antenna. When the wave is circularly polarized, the electric field vector appears to be rotated with all components losing the orientation. The mode of rotation may also be different at times. However, by using circular polarization, the effect of multi-path gets reduced, and hence it is used in satellite communication such as GPS. Another form of polarization is known as elliptical polarization. It occurs when there is a mix of linear and circular polarization. This can be visualized as before by the tip of the electric field vector tracing out an elliptically shaped corkscrew. Next, propagation modes. Basically, the different types of propagation modes are ground wave propagation, surface wave propagation is there, next space wave propagation is there, next sky wave propagation, next ionosphere is there. In ionosphere we are having the different types of layers, D layer, E layer, F layer, and F layer can be split into two, F1 layer and F2 layer. The frequencies are propagated, different frequency ranges are propagated in these layers. Ground wave propagation. It follows contour of the earth, is called ground wave propagation. It can propagate considerable distances. Frequency is up to 2 MHz. The best example for ground wave propagation is AM radio. Next, sky wave propagation. Signal reflected from the ionized layer of the atmosphere back down to earth. Signal can travel a number of hops back and forth between the ionosphere and the earth's surface. Hopping nothing but the signal is propagated between the two layers is called as the hopping. And reflection effect caused by refraction. Here we are getting the two concepts, reflection and refraction. Reflection nothing but the signal is reflected back to earth is called the reflection, and refraction nothing but the wave can propagate from one layer to another layer. That concept is called the refraction. For one layer to another layer, the refractive index is not similar. That's why the wave is in bent form. It can travel from one layer to another layer. The example for sky wave propagation is aperture radio and CB radio. Next, line of sight propagation. Transmitting and receiving antennas must be within the line of sight. That is, both are in the same height. So, refraction, bending of microwaves by the atmosphere. Velocity of electromagnetic waves is a function of the density of the medium. When the wave changes medium, speed is also changes. Wave bends at the boundary between mediums. The optical line of sight D equal to 3.57 into root h. Effective line of sight D equal to 3.57 into root of kh, where D equal to distance between antenna and the horizon expressed in kilometers, h equal to height of the antenna in meters, k equal to adjustment factor to account for refraction rule of the thumb, that is the k is equal to 4/3, we are using the constant, and a formula for to find the line of sight between the transmitting and receiving antenna is T maximum equal to 3.57 of root of k into h1 plus root of k into h2, where h1 equal to height of the antenna 1, that is transmitting antenna, h2 equal to height of antenna 2, that is a receiving antenna. Conclusion. All the antennas are very useful in all the applications such as transmitter and receiver. Antennas are used to convert electrical energy into electromagnetic signals. All these antennas are used for several applications, that is satellite communication, radar communication and television broadcasting signals. So this is about the brief view of the antennas and wave propagation or wave propagation. Thank you.